Good evening, everyone, and welcome to the Droning Professor. Tonight we're going to learn about the event horizon. So, as you make yourselves comfortable, please take a moment to let us know where you're listening from, and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. I'm genuinely thrilled you've chosen to spend the next hour and change with me discussing what is arguably the universe's most dramatic real estate boundary. Tonight we're going to talk about the event horizon, that invisible line in space where physics decides to get weird, where light gives up its day job, and where, quite literally, there is no coming back. This is the point of no return, and I promise you, by the end of this lesson, you'll never look at the night sky the same way again. Now, before we dive into the deep end of cosmic despair, black holes, let me set the stage. We're going to take a journey that spans centuries of human thought, from an 18th century English clergyman who had a remarkably dark imagination, to a German physicist scribbling equations in the trenches of World War I, all the way to a global network of radio telescopes that gave us humanity's first actual photograph of what surrounds a black hole. Along the way, we'll encounter spaghetti that you absolutely do not want to eat, time that slows to a crawl, and paradoxes that have kept physicists awake at night for 50 years. This is going to be a wild ride. Let's start with a simple question. What happens when gravity gets really, really strong? And by really strong, I don't mean drop your phone and crack the screen strong. I mean so strong that the very fabric of space and time warps, bends, and ultimately breaks down. To understand this, we need to go back to 1784, to a quiet English rectory where the Reverend John Michel was thinking thoughts that no one else would seriously consider for another 2 centuries. Michel was what we might call a polymath today, a geologist, an astronomer, and apparently someone with entirely too much time on his hands between Sunday sermons. He asked himself a question that seems obvious in retrospect, but was revolutionary at the time. What if a star were so massive that light itself couldn't escape from it? Now, Michel was working with Newton's theory of gravity and the corpuscular theory of light, which treated light as tiny particles. He knew about escape velocity, the speed you need to achieve to break free from a gravitational body. We all intuitively understand this. If you throw a ball up, it comes back down. Throw it harder, it goes higher. Throw it at about 11 kilometers per second, and it leaves Earth entirely. That's Earth's escape velocity. Michel did some calculations and realized that if you had a star with the same density as our Sun, but 500 times its radius, the escape velocity at its surface would exceed the speed of light. Light particles would be launched upward, slow down, and fall back like a baseball thrown toward the sky. The star would be completely invisible. He called these hypothetical objects dark stars. In a letter to Henry Cavendish that was published by the Royal Society, Michel wrote about objects from which light could not arrive at us. He even suggested that we might detect these invisible stars by watching for the gravitational effects they'd have on visible companion stars orbiting them. This is precisely how we detect black holes today, 240 years later. The man was ahead of his time by centuries, and yet if you ask the average person today if they've heard of John Michel, they'd probably assume he's a jazz musician. A dozen years later, the French mathematician Pierre-Simon Laplace independently came up with essentially the same idea. Laplace was considerably more famous than Michel, so for a while, dark stars were discussed in academic circles. But then something happened that put the whole concept on ice for over a century. Scientists discovered that light behaves like a wave, not a particle. If light is a wave, the reasoning went, gravity shouldn't affect it. Waves aren't pulled down by gravity like baseballs are. You don't see ocean waves slowing down and falling back toward the center of the Earth. So the idea of dark stars was abandoned, filed away as a curious mistake. This is one of those beautiful moments in science where everyone was wrong in exactly the right way. Light does behave like a wave, but gravity doesn't just pull on objects. As Einstein would show us, gravity warps space and time themselves. Light follows the curves of space-time, so it is affected by gravity just not in the way Newton imagined. Michel and Laplace were right for the wrong reasons, and the scientists who dismissed them were wrong for the right reasons. Science is messy like that. Now, fast forward to 1915, Albert Einstein, after a decade of work that included 4 of the most productive years in scientific history, publishes his general theory of relativity. The central insight is elegant and mind-bending. Gravity isn't a force in the traditional sense. Instead, massive objects curve the fabric of space-time, and other objects, including light, follow these curves. The planets don't orbit the sun because they're being pulled by an invisible rope. They're following the curved paths created by the sun's mass, distorting the geometry of space around it. If you want a visual, imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, and if you roll a marble nearby, it curves toward the bowling ball. That's roughly what massive objects do to space-time, although the real situation involves 4 dimensions and mathematics that would make your head spin faster than a pulsar. Here's where it gets interesting. Less than a month after Einstein published general relativity, a physicist named Karl Schwarzschild found an exact solution to Einstein's field equations. Now, Einstein himself had only managed approximate solutions. He actually believed exact solutions might never be found. But Schwarzschild, who was serving in the German army on the Eastern Front during World War I, somehow found time between artillery barrages to do some of the most important mathematics in the history of physics. Talk about working under pressure. Schwarzschild's solution described the gravitational field around a perfectly spherical, non-rotating, uncharged mass. And buried in his equations was something peculiar, a special radius at which the mathematics broke down. At this radius, which we now call the Schwarzschild radius, something strange happens to space and time. The formula for the Schwarzschild radius is beautifully simple. It equals 2 times the gravitational constant times the mass, divided by the speed of light squared. In symbols, that's r sub s equals 2gm over c squared. What this tells us is that the Schwarzschild radius is directly proportional to mass. Double the mass, double the radius. Triple the mass, triple the radius. It's one of the most elegant relationships in all of physics. Let me give you some numbers to make this concrete. For our sun, the Schwarzschild radius is about 3 kilometers. That's it. If you could somehow compress all the mass of the sun, 1.99 times 10 to the 30th kilograms, into a sphere just 3 kilometers across, light would not be able to escape from its surface. For Earth, the Schwarzschild radius is about 9 millimeters. Your car keys have a Schwarzschild radius smaller than a proton. Now, the sun is never going to become a black hole. Neither is Earth. They simply don't have enough mass for gravity to overcome the other forces that hold them up against collapse. The sun will eventually run out of hydrogen fuel, swell into a red giant, and then shed its outer layers to become a white dwarf, a dense stellar corpse supported by electron degeneracy pressure. Earth will presumably be vaporized somewhere in this process, which should give you perspective on your long-term planning. But for stars significantly more massive than the sun, roughly more than 20 times its mass, a different fate awaits. When such a star exhausts its nuclear fuel, there's nothing left to counterbalance gravity. The core collapses catastrophically. If the remaining mass is between about 1.4 and 3 solar masses, you get a neutron star, an object so dense that a teaspoon of its material would weigh about 6 billion tons. But if the collapsing core exceeds roughly 3 solar masses, even neutron degeneracy pressure can't stop the collapse. Gravity wins completely, and a black hole is born. This brings us to the main character of tonight's story, the event horizon. The event horizon is not a physical surface. You couldn't stand on it, touch it, or see it if you were floating nearby. It's a mathematical boundary, a conceptual line in the sand, or rather, in space-time. The term event horizon was coined in 1956 by the Austrian physicist Wolfgang Rindler, who described it as a frontier between things observable and things unobservable. That's a remarkably poetic description for what is essentially a point of cosmic censorship. At the event horizon, the escape velocity equals exactly the speed of light. Inside this boundary, to escape the black hole, you would need to travel faster than light, which, according to everything we know about physics, is impossible. Once you cross the event horizon, your future contains only one destination, the singularity at the center of the black hole. It's not that you can't escape because you're being pulled too hard. It's that all paths through space-time, every possible trajectory you could take, lead inward. Trying to escape from inside a black hole is like trying to walk back to yesterday. The direction out simply doesn't exist anymore. This is one of the most profound conceptual shifts that general relativity forces upon us. Inside the event horizon, space and time essentially swap roles. The radial direction, the direction toward or away from the singularity, becomes time-like, while time becomes space-like. Falling toward the singularity isn't like falling toward Earth. It's more like being carried inexorably toward tomorrow. You can no more stop your fall toward the singularity than you can stop Tuesday from arriving. In 1958, physicist David Finkelstein provided a clearer interpretation of what the event horizon really means. He called it a perfect unidirectional membrane. Causal influences can cross it in only one direction. Things can fall in, but nothing, not matter, not light, not even information can get back out. It's the universe's ultimate roach motel. Now, here's something that confuses a lot of people. The event horizon is not where things get crushed or destroyed. It's not where the extreme gravitational effects happen. In fact, for a sufficiently massive black hole, you could cross the event horizon and notice absolutely nothing unusual. The curvature of space-time at that point might be gentle enough that your body wouldn't experience any significant stress. You'd be doomed, of course, there's no coming back, but you wouldn't know it from local measurements. The event horizon is, as physicists say, locally unremarkable. This is counterintuitive, so let me explain it another way. Gravity itself isn't what kills you near a black hole. What kills you is tidal forces, the difference in gravitational pull between different parts of your body. If your feet are closer to the black hole than your head, they're being pulled more strongly. This differential creates a stretching force that, in extreme cases, will pull you apart like taffy. The strength of these tidal forces depends on the mass of the black hole and how close you are to the center. Crucially, for a given distance from the center, smaller black holes have stronger tidal forces than larger ones. This seems backward, doesn't it? But it makes sense when you think about it. A stellar mass black hole, say, 10 times the mass of the Sun, has a Schwarzschild radius of about 30 kilometers. The event horizon is very close to where all that mass is concentrated, so the tidal forces there are ferocious. But a supermassive black hole with 100 million solar masses has a Schwarzschild radius of about 300 million kilometers, roughly twice the distance from Earth to the Sunday. At that scale, the event horizon is so far from the center that the tidal forces there are actually weaker than what you experience standing on Earth. Let me give you some numbers that really drive this home. For a stellar mass black hole of about 1 solar mass, the tidal acceleration at the event horizon, the stretching force between your head and feet, would be about 19.6 billion meters per second squared. That's roughly 1 billion times the gravity on Earth's surface. You wouldn't just die, you'd be converted into a stream of subatomic particles before you got anywhere close to the event horizon. But for a supermassive black hole of 100 million solar masses, the tidal acceleration at the event horizon is about 0.000019 meters per second squared. That's less than the tidal force you feel right now from the moon. You could cross that event horizon and feel perfectly fine for a little while. Of course, as you continued falling inward, the tidal forces would increase, and eventually you'd still be ripped apart. But the point is that crossing the event horizon itself wouldn't be the traumatic experience you might imagine. This leads us to one of the more colorfully named phenomena in all of physics: spaghettification. I swear I'm not making this up. The term was popularized by Stephen Hawking in his book A Brief History of Time, and it describes exactly what happens to an object falling into a stellar mass black hole. The extreme tidal forces stretch you vertically while compressing you horizontally. You're pulled into a long, thin strand like spaghetti. Not the most dignified way to go, but at least it's quick. Hawking described it this way. Imagine an unfortunate astronaut falling feet first into a black hole. The gravity at their feet is significantly stronger than at their head. This difference stretches them out. Meanwhile, because all parts of their body are being pulled toward the same point, the singularity, the parts of their body that are side by side are being squeezed together. The astronaut is simultaneously stretched lengthwise and compressed widthwise until they're turned into a long, thin stream of particles, accelerating toward the center of the black hole. But here's the really strange part. From the astronaut's perspective, this all happens very quickly. They cross the event horizon, experience spaghettification, and hit the singularity in a matter of seconds or less. From the perspective of an outside observer, however, the astronaut never crosses the event horizon at all. Welcome to the bizarre world of gravitational time dilation. Einstein's general relativity tells us that time passes more slowly in stronger gravitational fields. This isn't just a theoretical prediction, it's been measured countless times with atomic clocks. A clock at sea level runs slightly slower than a clock on top of a mountain. The GPS satellites orbiting Earth have to account for this effect. If they didn't, your navigation would be off by several kilometers per day. Near a black hole, this effect becomes extreme. As an object approaches the event horizon, time as measured by a distant observer slows down more and more. At the event horizon itself, time stops completely from the outside perspective. The object appears to freeze, redden as its light is stretched to longer and longer wavelengths, and fade away as the photons it emits become too weak to detect. But the object never quite crosses the boundary. It hangs there, seemingly forever, asymptotically approaching but never reaching the horizon. This is why physicist John Wheeler, who coined the term black hole in 1967, initially called these objects frozen stars. From the outside, a collapsing star would appear to freeze at its own event horizon, never completing its collapse. But from the falling object's perspective, everything is different. The astronaut falls through the event horizon without noticing anything special. Their watch keeps ticking normally. They might look back and see the outside universe, though the light would be blue-shifted, compressed to shorter wavelengths by their motion toward it. But they wouldn't see the entire future history of the universe flash before their eyes, as some popular accounts suggest. That's a misconception. They'd simply fall in, experience the increasing tidal forces, and meet their end at the singularity, all in a finite and rather brief amount of time. This apparent contradiction, the outside observer sees the astronaut freeze forever at the horizon, while the astronaut experiences falling through and hitting the singularity, is not a paradox. It's just relativity being relativity. Different observers have different experiences of time and space. Neither view is correct in some absolute sense. Both are valid descriptions of the same physical process from different reference frames. Let me take a moment to talk about what's actually inside a black hole, or rather, what we think might be inside, because no information can ever escape to tell us for sure. At the very center of a black hole, according to general relativity, lies the singularity. This is where all the mass of the black hole is concentrated into a single point of infinite density. Space and time curve infinitely. The laws of physics as we know them break down completely. It's not that we don't understand what happens at the singularity, it's that our current theories literally cannot describe it. The mathematics gives us infinities and nonsense. When physicists encounter infinities in their equations, it usually means the theory is missing something, that there's some new physics we haven't discovered yet. Most physicists believe that quantum mechanics must play a role at the singularity. General relativity is a classical theory. It doesn't incorporate the quantum nature of reality that governs the very small. We expect that a complete theory of quantum gravity, which we don't yet have, would replace the singularity with something finite, though possibly no less strange. String theory suggests the singularity might be a tiny, vibrating knot of higher dimensional structures. Loop quantum gravity suggests space itself is quantized into discrete chunks that can't be squeezed infinitely small, but these are educated guesses at best. The event horizon, in a sense, protects us from the singularity. It acts as a cosmic curtain, hiding the breakdown of physics from the rest of the universe. Roger Penrose formalized this idea in 1969 with what's called the cosmic censorship conjecture. The strong version says that nature forbids naked singularities, singularities not hidden behind an event horizon. The universe apparently is modest about its mathematical misbehavior. Now, I've been talking about black holes as if they're simple objects, but they can actually come in several varieties. The simplest kind, described by Schwarzschild's solution, doesn't rotate and has no electric charge. It's completely characterized by a single number, its mass. The event horizon is a perfect sphere. Real black holes, formed from rotating stars, are expected to rotate, and often quite fast. A rotating black hole is described by the Kerr solution, found by New Zealand mathematician Roy Kerr in 1963. Rotating black holes have some additional structure. The event horizon is still present, but it's slightly flattened at the poles, like a tangerine. Surrounding the event horizon is a region called the ergosphere, where space-time itself is dragged around by the black hole's rotation, a phenomenon called frame dragging. In the ergosphere, you cannot stay still even if you wanted to. You're forced to rotate with the black hole, though you can still escape if you're outside the event horizon. The ergosphere has a remarkable property. It's possible to extract energy from a rotating black hole. Roger Penrose showed that if you send an object into the ergosphere and split it in two, one piece can fall into the black hole while the other piece escapes with more energy than the original object had. This energy comes from the black hole's rotation, which slows down slightly as a result. In principle, you could use this process called the Penrose process to extract up to 29% of a rotating black hole's mass energy. That's an extraordinarily efficient power source, though the engineering challenges would be considerable. Black holes can also be classified by their mass. Stellar mass black holes, formed from collapsed stars, range from about 3 to a few dozen solar masses. The most massive stellar black hole currently known has about 21 solar masses, though gravitational wave observations have detected black hole mergers resulting in objects of 60 or more solar masses. At the other extreme are supermassive black holes, found at the centers of most large galaxies. These monsters contain millions to billions of solar masses. Our own Milky Way hosts Sagittarius A star, that's Sagittarius A with an asterisk pronounced A star, a supermassive black hole of about 4 million solar masses. It's located about 26,000 light-years away, at the galactic center. Don't worry, at that distance it poses no threat to us. You might as well worry about a shark in an aquarium in Tokyo. The supermassive black hole at the center of the galaxy, Messier 87, is in another league entirely. M87 star, that's M87 with an asterisk, weighs in at 6.5 billion solar masses. Its event horizon would extend well beyond the orbit of Pluto if it were placed in our solar system. And on April 10, 2019, the Event Horizon Telescope collaboration revealed the first direct image of this Leviathan. Let me tell you about that image, because it represents one of the most remarkable achievements in the history of astronomy. The Event Horizon Telescope isn't a single instrument. It's a global network of radio telescopes, synchronized with atomic clocks and spread across multiple continents, from Hawaii to Spain to the South Pole. By combining data from all these telescopes using a technique called very long baseline interferometry, the collaboration effectively created a telescope the size of Earth. This was necessary because the target, the shadow of M87 star, spans an angle of only about 42 micro-arcseconds across the sky. That's roughly the angular size of a donut on the moon as seen from Earth. Or, to put it another way, if you could see that well, You could read a newspaper in New York from a cafe in Paris. The observations took place in April 2017. The telescopes collected about 5 petabytes of data, more than could be transferred over the internet in any reasonable time. Instead, the data were physically shipped on hard drives to 2 central processing locations. Then came 2 years of painstaking analysis, cross-checking, and verification. What they saw was a bright ring of light surrounding a dark central region. The ring is emission from hot, glowing matter, gas heated to billions of degrees, orbiting the black hole just outside its event horizon. The dark region is the black hole's shadow, about 2.5 times larger than the event horizon itself because of how light is bent by the extreme gravity. The ring isn't uniformly bright. It's brighter on one side than the other. This is because the matter is orbiting at nearly the speed of light, and relativistic effects make the approaching side appear brighter while the receding side appears dimmer. This asymmetry tells us the direction of rotation and the orientation of the black hole's spin axis. In May 2022, the collaboration released an image of our own galactic center black hole, Sagittarius A star. Despite being 1,000 times less massive than M87 star, it appears roughly the same angular size because it's 1,000 times closer. Imaging it was actually harder, though, because the matter orbiting Sagittarius A star completes an orbit in mere minutes rather than days, meaning the appearance changes rapidly during observations. These images represent something almost metaphysically significant. We have directly observed the boundary of a black hole, the edge of a region from which nothing can escape. We've taken a picture of the point of no return, but I've been focusing on what happens to objects falling into black holes. What about the black holes themselves? Do they last forever? This brings us to Stephen Hawking's most famous discovery. Black holes evaporate. In 1974, Hawking made a startling prediction by applying quantum mechanics to the curved spacetime near a black hole's event horizon. According to quantum field theory, empty space isn't really empty. It's a seething foam of virtual particles, pairs of particles and antiparticles constantly popping into existence and annihilating each other. Normally, these virtual particles exist for so briefly that they have no measurable effect. But at the event horizon, something strange happens. If a virtual particle pair forms right at the boundary, one particle might fall into the black hole while the other escapes. The escaping particle carries positive energy away from the black hole, while the infalling particle, due to the strange geometry near the horizon, carries negative energy into it. The net effect is that the black hole loses mass. From a distance, the black hole appears to emit thermal radiation with a temperature inversely proportional to its mass. This is Hawking radiation. The larger the black hole, the colder it is. The smaller the black hole, the hotter it gets. A stellar mass black hole has a temperature of about 60 billionths of a Kelvin, far, far colder than the cosmic microwave background radiation that fills the universe. Such a black hole absorbs more energy from its surroundings than it emits and will actually grow over time, not shrink. But in principle, if a black hole were completely isolated and could emit Hawking radiation without absorbing anything, it would very slowly lose mass. As it loses mass, it gets smaller. As it gets smaller, it gets hotter. As it gets hotter, it radiates faster. The process accelerates until, at the very end, the black hole undergoes a final explosive burst of radiation and vanishes entirely. How long does this take? For a stellar mass black hole, the evaporation time is approximately 10 to the 67th power years. That's a 1 followed by 67 zeros. The current age of the universe is about 14 billion years, or roughly 10 to the 10th power years. Black hole evaporation operates on timescales so vast that they make the current age of the universe look like the blink of an eye. For supermassive black holes, the evaporation time is even longer, up to 10 to the 100th power years or more. These numbers are essentially meaningless in human terms. But what they tell us is profound. Black holes are not eternal. Given enough time, more time than atoms will remain bound in molecules, more time than protons might survive, even black holes will fade away. Hawking radiation creates a profound puzzle known as the black hole information paradox, and this has kept theoretical physicists arguing for 50 years. The paradox goes like this. In quantum mechanics, information cannot be destroyed. The laws of physics are deterministic in a certain sense. If you know the exact quantum state of a system, you can in principle calculate what it will become in the future or what it was in the past. Information is preserved. But when matter falls into a black hole, and then the black hole evaporates via Hawking radiation, what happens to the information about that matter? Hawking's original calculation suggested that the radiation is purely thermal random, like the glow from a hot coal. It doesn't encode any information about what fell in. The black hole could swallow an encyclopedia or a television set, and the Hawking radiation would be identical. The information appears to be destroyed. This was troubling because it suggests either quantum mechanics is wrong, which would upend virtually all of modern physics, or our understanding of black holes is incomplete. Hawking initially argued for information loss, famously betting against other physicists like John Preskill. In 2004, Hawking conceded the bet, acknowledging that information is probably preserved, though exactly how remained unclear. In 2012, the paradox got even more complicated. Physicists Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, often abbreviated as AMPS, showed that attempting to preserve information while maintaining other seemingly reasonable assumptions led to a contradiction. Their resolution suggested that the event horizon might actually be a firewall, a violent energetic barrier that would incinerate anything crossing it. This was troubling because it contradicted Einstein's equivalence principle, which says that free fall should be indistinguishable from floating in empty space. If you're falling into a sufficiently large black hole, you shouldn't notice anything special at the horizon. But a firewall would definitely count as something special. Theoretical physicist Raphael Bousso complained that a firewall simply can't appear in empty space, any more than a brick wall can suddenly appear in an empty field and smack you in the face. And yet the mathematical arguments for firewalls were hard to dismiss. The firewall debate spawned countless papers, conferences, and sleepless nights. Various resolutions have been proposed. Some suggest that information is encoded in subtle correlations in the Hawking radiation that become apparent only when you have all of it. Others propose that the black hole interior doesn't exist as a separate region of space-time, that what looks like falling through the horizon is equivalent to being absorbed into a holographic boundary. Still others suggest that our entire framework for thinking about space-time inside black holes is wrong. As of now, there's no consensus. The information paradox remains one of the deepest unsolved problems in physics, pointing toward the eventual unification of quantum mechanics and gravity. Let me take us now on a visual journey. What would you actually see if you approached a black hole? From a distance, a black hole with an accretion disk, that hot, swirling disk of matter falling in, would look like nothing you've ever seen. The disk wouldn't appear flat. Gravitational lensing would warp it into strange shapes. You'd see the disk behind the black hole bent up over the top and down under the bottom, creating a kind of halo effect. Light from parts of the disk on the far side of the black hole would curve around and reach your eyes after completing partial orbits. At a distance of 1.5 times the Schwarzschild radius lies the photon sphere, a region where light can orbit the black hole. This isn't a stable orbit. The slightest perturbation would send a photon either spiraling into the black hole or escaping to infinity. But mathematically, there's a shell around every black hole where photons travel in circles. If you could hover at the photon sphere, which would require an impossibly powerful rocket, you could look forward and see the back of your own head. Light leaving the back of your skull would travel around the black hole and enter your eyes. Of course, you'd also be bathed in all the radiation that's collected there, visible light, but also X-rays and gamma rays at lethal intensities. It wouldn't be a comfortable place to sightsee. As you approach closer, the the black hole's shadow would grow to fill more and more of your visual field. The distant stars would appear to crowd together, compressed by the gravitational lensing into a smaller and smaller region behind you. Multiple images of the same stars would appear as light takes different paths around the black hole. If you were falling toward a stellar mass black hole, the increasing tidal forces would eventually tear you apart. But if you were falling toward a supermassive black hole, you might pass the event horizon without any dramatic event. The last thing you'd see would be the outside universe, increasingly blue-shifted as you accelerate toward it, though toward has lost much of its meaning by this point. Inside the event horizon, your future is fixed. No matter which direction you try to travel, you're headed for the singularity. The very structure of space-time funnels you inexorably inward. How long would this take from your perspective? For a black hole like Sagittarius A star, roughly 16 seconds. You'd have 16 seconds to contemplate the meaning of existence before reaching a point where physics as we understand it ends. Before I conclude, let me mention something that connects black holes to the grandest questions about the nature of reality. In the 1990s, physicists Juan Maldacena, Gerard Hooft, and Leonard Susskind developed what's called the holographic principle. This remarkable idea suggests that all the information contained in a volume of space can be represented on the boundary of that space, like a hologram that encodes a three-dimensional image on a two-dimensional surface. For black holes, this means that all the information about what fell in might be encoded on the event horizon, not lost inside, but smeared across the surface in some unimaginably complex pattern. The event horizon would contain a complete description of the black hole's contents, just written in a language we don't yet know how to read. Some physicists take this further, suggesting that our entire universe might be a holographic projection from some distant boundary. The three-dimensional reality we experience could emerge from two-dimensional information encoded on a surface we can't perceive. If this sounds like science fiction, well, it's science fact, or at least science-serious theoretical investigation. The holographic principle has passed numerous mathematical consistency checks and is considered a major clue about the nature of quantum gravity. Black holes, it seems, are not just fascinating objects in their own right. They're windows into the deepest structure of reality laboratories where quantum mechanics and gravity collide, where information theory meets thermodynamics, where space-time itself might give way to something stranger and more fundamental. So where does this leave us? We've traveled from John Mitchell's rectory to Einstein's relativity, from Schwarzschild's trenches to Hawking's radiation. We've encountered event horizons and singularities, spaghettification and time dilation, firewalls and information paradoxes. We've seen how a global collaboration of telescopes can photograph something that, by definition, cannot be seen directly. The event horizon remains one of the most profound concepts in all of physics. It's a boundary that isn't really there, a surface with no substance, a point of no return that's everywhere and nowhere. It marks the edge of the knowable universe, beyond which our theories break down and our imaginations strain. And yet, despite their alien nature, black holes are all around us. There are likely hundreds of millions of stellar mass black holes in our galaxy alone, and a supermassive one sits at the center of virtually every large galaxy we've observed. They're not exotic curiosities. They're fundamental components of cosmic architecture. Without black holes, galaxies might not form the way they do. Without the gravitational stirring of these cosmic monsters, the universe might look profoundly different. We live in a cosmos where points of no return are not just philosophical concepts but physical realities. Where time can slow to a stop and space can curve back on itself, where falling toward the center of something can become as inevitable as flowing toward the future. The next time you look up at the night sky, consider this. Hidden among those points of light are regions where light itself cannot escape, invisible objects that shape the destiny of galaxies. Points of no return scattered like seeds across the vast darkness. And we small, fragile, curious creatures on an ordinary planet around an ordinary star, we figured this out. We wrote down equations and built telescopes and argued about information paradoxes, and we pulled back the curtain on some of the universe's deepest secrets. That, if you ask me, is worth getting out of bed for. Good night, everyone. Don't get too close to any black holes on your way home. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.